it has a lot of memory. And then once you have the pre-computed tables, you actually encrypt using them, and that's how you get the best performance. Okay, so if you have to send an implementation of AES over the network, you can kind of get the best of all worlds, where the code over the network is small, but when it reaches the target client, it can kind of inflate itself and then get the best performance as it's doing encryption on the client. Now, AES is such a popular block cipher. Now, essentially, when you build crypto into products, essentially you're supposed to be using AES. And as a result, Intel actually put AES support into the processor itself. So since Westmere, there are special instructions in the Intel processor to help accelerate AES. And so I listed these instructions here. They come in two pairs, AES enc and AES enc last, and then there's AES keygen assist. So let me explain what they do. So AES enc essentially implements one round of AES, namely apply the three functions in the XOR with the round key. And AES enc last basically implements the last round of AES. Remember, the last round didn't have the mixed columns phase. It only had the subs bytes and shift rows. And so that's what AES enc last does. And the way you call these instructions is using 128-bit registers, which correspond to the state of AES. And so you would have one register containing the state and one register containing the current round key. And then when you call AES enc on these two registers, basically they would run one round of AES and place the result inside of this XMM1 state register. And as a result, if you wanted to implement the whole AES, all you would do is you would call AES enc 9 times, and then you would call AES enc last 1 time, and these 10 instructions are basically the entire implementation of AES. That's it. It's that easy to implement AES on this hardware. And they claim because these operations are now done inside the processor, not using external instructions, they're implemented in the processor, they claim that they can get a 14x speed up over, say, an implementation that's running on the same hardware, but implementing AES without these special instructions. So this is quite a significant speed up, and in fact there are now lots of products that make use of these special instructions. And let's just say that this is not specific to Intel. If you're an AMD fan, AMD also implemented exactly kind of similar instructions in their Bulldozer architecture and further in future architectures. Okay, so let's talk about the security of AES. I want to mention just two attacks here. Obviously, AES has been studied quite a bit, but the only two attacks on the full AES are the following two. So first of all, if you wanted to do key recovery, the best attack basically is only 4 times faster than exhaustive search, which means that instead of a 128-bit key, really you should be thinking of AES as a 126-bit key, because exhaustive search really is kind of 4 times faster than it should. Of course, 2 to the 126 is still more time than we have to compute, and this really does not hurt the security of AES. The more significant attack actually is on AES 256. It turns out there's a weakness in the key expansion design of AES, which allows for what's called a related key attack. So what's a related key attack? Essentially, if you give me about 2 to the 100 input-output pairs for AES, but from 4 related keys. So these are keys that are very closely related. Namely, key number 2 is the same as key number 1, except that a few bits of key number 1 have been flipped. Similarly, key number 3 is the same as key number 1, except that a few bits are flipped, and the same for key number 4. These are very closely related keys. If you like, their Hamming distance is very short. But if you do that, then in fact, there is a 2 to the 100 attack. Now you should say, well, 2 to the 100 is still impractical. This is still more time than we can actually run today. But nevertheless, the fact that it's so much better than an exhaustive search attack is so much better than 2 to the 256 is kind of a limitation of the cipher. But generally, it's not a significant limitation because it requires related keys. And so in practice, of course, you're supposed to be choosing your keys at random so that you have no related keys in your system, and as a result, this attack wouldn't apply. But if you do have related keys, then there's a problem. So this is the end of the segment, and in the next segment, we're going to talk about more provably secure constructions for block ciphers.